क्लास एक्सटेंड हो गई वो चलता है भाई, लेकिन डिस्कशन करने में मजा आना चाहिए। ठीक है आपका स्क्रीन, ठीक है। So I'll give you a hypothetical situation. So the hypothetical situation is very, very simple. Recording is हाँ, ठीक है. So the hypothetical situation that we're talking about, it's not related to any of the things that I was anyway going to cover. It's like totally out of the box. We'll just spend 10-15 minutes on only discussing it. Okay. So the idea is, say we have a gigantic monolith. Okay. Monolith, this is a typical API server that serves REST API /me/payment, etc., etc., etc. Like so many of them. Then there are one master database and let's say two replica database. Okay, and these database are in sync through normal master replica replication. Okay. Now the problem is there is already shit ton of code written in the system. Well, far too much of code, like just doesn't like more than 1 lakh, more than 100,000 lines of code. Okay, which is legacy, not the new one. Okay, legacy code. Now the problem that happened is this monolithic database is, and here what we are doing is we are doing client side sharding. So my client, so basically my monolith API would know what all database exist, and it would be making connection to those database and would be firing the queries. So for example, my monolithic API, let's say I want to get user profile information. So my monolith API would know that this is a user profile information, and while making a query, it would make a query to one of the replicas and then get the result, and not basically trouble the master to get the data, because master is there to take all the writes. Right. So now get user profile explicitly goes to replica, replica 1. Okay, because this is written in the code, like hard coded, use this connection to go to the database and fetch the data. Now what has happened is a lot of legacy code is using master as my connection string. So it is using master DB. So the problem is my legacy code uses master as connection. So even for read queries, like let's say get user profile is explicitly configured to go to replica 1. But let's say get course info, it goes to master because that's a legacy code. And similar to this, there are like thousands and thousands of places where similar to this legacy code is written. Right, key. This is what exactly happens. Like I'm using a default connection object, and this default connection object connects to master. And since this is connecting to master, there are thousands of instances like this. Now what the problem is that since my master, whose job was to like typically handle all the writes, now what is happening is my legacy code read queries are also going to master. Right now, those read queries that goes to the master is making my master choke. Right, because they could very well be served through replica 1 and replica 2, but they're not being served. And because in the code it is written that use this connection, and that connection is master connection, and it is there. Right now, the way to address this problem would be to see that, okay, this is my API request, and now this API request is making call to database and it's getting the data. So I can either go through all of my legacy code, find all the instances, and see if it requires to go to master or to go to replica. Right now, that is a very naive way to do it, to like go through all the SQL queries that I'm firing, or go through all the REST endpoints that I have, and then basically go on to the code and find which database it is connecting, and if it really needs to connect to master or not. Now, given this takes a lot of time to do it, right? Because you have to go through all the legacy code. You don't know the functionality. The team is changed. Like so many complexities have come up. Now, what would be your solution to this problem? Where what we have to do is we want to reduce the number of reads that go to the master and let them get served through replica. Okay, this is what the problem is. Now, how would you solve it? So what do we want? The goal is very simple. We would want rather unnecessary reads to not go to master and should be redirected to, or should be served from replica. But how would we do that?
We can add a load balancer. Can we add load balancer between?
Yeah, you can do anything. Let's just discuss that, because this is a very interesting problem to have. And the kind of hack we applied is like really interesting. I was not someone who actually came up with this. One of the technical architects in the team came up with this, and it was like really amazing of a solution. That's why I just wanted to like just discuss around this. And one thing, what do we have in the system is we also have an API gateway sitting in front. We already have this. So request comes to API gateway forwards it to our monolith API, and from there it serves the request and all. It hits the database master, replica 1, replica 2, depending on what is written in the code, and it goes there and it gets the data and it sends back to the cloud. Okay, chalo. How would we address the problem? Let's brainstorm. Yeah, Anshuman?
Yeah, I have a caching layer
Caching layer? Why?
In front of DB for reads.
Caching is already there. Caching is already there, right? But then the cache misses, they go to either of your database, right? Wahan pe there is a problem. Yeah, Amrish?
I think one may be like we can create connection pools for master and separate, and for
That is already there.
okay, it's already
It is
there.
already there. So the problem is we have to reduce. So the right now the main problem is we cannot go through 100,000 lines of legacy code
Mhm.
to move traffic from master to replica, because we would have to go through their code, understand the business logic, and then make that change.
Mhm.
Right? We have to do this fast. And like let's brainstorm, and then I'll tell all the advantages and disadvantages of the process.
We can add a
Just
load
to
balance.
confirm,
Yes, sir.
I mean, at the API gateway level, if it's a write API, I mean, have two monoliths, one for read and one for write. And at the API gateway level, and you just configure the read monolith API with the read replicas instead of, and once the write monolith will have the proper ones, and the read monolith will only have the read replicas, and at the API gateway level, you can actually redirect the traffic.
That's exactly what we did. Great, Varun. Thanks, Varun. That is exactly what we did. So now that already Varun has spoiled the fun, so the idea what we did was instead of having one monolith API, we created a parallel setup, right? So our setup now looks like this. So we have our request from end users coming in. It goes to our API gateway. Okay. Behind this, we instead of having one monolith configuration, we have the same code running two monolith parallel setup. Okay. So now API gateway pay, this is what it is configured. Okay. Now monolith one is the legacy one which is running. Now this legacy one, what it does is it reads something from a configuration store. Now this config is something that we did not alter. So whatever code is there, it is there and it is being served. So it goes and connects to the database that it has to connect. So let's say this is master replica 1, replica 2. It connects to whichever database it has to, and then it sends it. Right? Now, in our parallel setup of monolith 2, what we did is we changed the configuration and the database connection string that we provide in the default part as well, right? So the way we are serving configuration is like we have a remote configuration store. So whenever my API server starts up, it checks which configuration it has to load. It goes there and it loads that configuration. So now this configuration was called as API sort of stuff. So it took that API configuration, usme it found the database connection string. It found 3 database configuration string, right? So for master, for replica 1, for replica 2. For monolith 2, what we did was we created a copy of the config. So it is actually a copy of existing config with one change in the default one. So which was connected to master, this one only connects to replica 1 and replica 2. It does not connect to master. So let's say our configuration was written like this, like default db replica 1 and replica 2. So this is how our DB connections are stored. And here you have like username, password, connection string, etc., etc. Similar to this, we have for this 3. The only change being this is U1, P1, C1, U2, P2, C2, U3, P3, C3. Now, this was the legacy configuration. Now, this legacy configuration was then changed to, let me just copy this and paste. So this was changed to, because the default one was the one which was connected to master. This we changed to this. So all of our requests of default DB for my monolith 2. So this was my mono 1. This is my mono 2. So default of mono 2, instead of pointing to this one for master, like U1, P1, C1, and this actually goes to replica because it's U2, P2, C2. So without changing any code, we created a parallel setup of mono 1 and mono 2. Just that we copied the entire config of mono 1, copy pasted it into mono 2. Now this config may, instead of pointing it to master, so we had 3 connections, one master, one replica 1, one replica 2. So the master connection string ka jo username password hai, that got changed, we changed it to replica 1. So now any request that was connecting to default DB for mono 1 will hit master, but default DB for mono 2 will hit replica 1. Right. So this way, even if I'm making any write calls, they would fail, right? Because my replica is a read replica which would not entertain update queries. It would not. So those would fail. But we would know that what we can do is, with this kind of setup, we can now configure, like let's say we know that /me API is a read-only API. It does not need to do any update. So in API gateway, we can configure /me API should go to monolith 2. Let's say payments API. We know that payments API requires write. So let's say I have /payments API and I can configure it to go to monolith 1. And then we can have a star rule that says redirect everything to monolith 1. Okay, so now basically star becomes my catch-all. So if none of the rules match, forward everything to monolith 1, which means my existing setup would work exactly the same as my legacy setup with no problem whatsoever, right? But now I can add specific conditions. I can add specific conditions like /me should go to monolith 2. Now when it goes to monolith 2, the same code runs in, but the default DB connection that was connecting to master, in this configuration it would connect to replica. So without any code change, without anything, we are now in a process of slowly and steadily adding rules. So then we would still have to go through the code base, and we would still have to go through like which are there. But instead of doing it at the code level, because like there might be a lot of dead code in the system, It's a lot of legacy or a lot of APIs which are not even being called at all. So slowly and steadily we can then I go through API by API and then start adding this rule. Okay, this API should go to monolith 2, this API should go to monolith 1. And this is what we structured. And now we are in that process. So we basically got some breathing space to, like basically 1 month ka runway mil gaya to like delay our optimization by going through the code. And now we are basically slowly tackling the problem. Yeah, Amrish?
So, is there way to specify method level at the load balancer here?
At the API gateway level?
Yeah.
Yeah, in the API gateway, you can actually configure rules. Ki if my URL is this,
And method.
forward it to this.
No, URL is fine. Can we
Hmm.
do like if it's all are following the Rust standard, like from that we can
Typically,
make
no, because you can't do it at method level. Na?
okay.
Method level kahan se kare? Because all your REST server only understands URL, and the
Okay.
methods are configured within that. So it
Mhm.
is part of the process.
Okay, I thought that from request, if somehow we can extract the method,
No, request में से method नहीं निकल सकते.
we can't.
It would become really tough. Yeah.
Okay.
Right. So now we have bought ourselves some time.
And
Steadily we'll do that.
second question is for let's say we have these replicas, so each monolith server will do the round robin here for forwarding.
A monolith setup. So monolith 1 is not just one API server. Monolith 1. So depending on whatever it is written. So it is client side sharding. So in some cases we are using connection of R2. In some cases we are using connection of R1, depending on the kind of workload we would have to throw there.
Okay.
Yeah, Bhupendra?
For this API gateway, did you like write the service or is it a like
No,
some
API gateway we are basically using Kraken D here.
what is it?
Kraken, KRAKEN-D.
Okay, it's a standard service.
It's yeah. So it's one of a popular open source thing called Kraken D. So we are using that only. We have not written anything fresh here.
Okay.
Chala. I'm basically something interesting which I worked like which I found yesterday. So I just thought let's share it with you guys because this was a very interesting solution. Like without actually changing any piece of code, just copy pasting entire config, replicating our infrastructure. We are able to buy some time and like handle it on the side of API gateway. Although not optimal, but at least a lot of we can immediately start seeing improvements in response time because like our master would be free from all the junk stuff that it has to handle. Nice. Coming back to the spillover from the last week, storage engines ka S3 because this is a big design. So that's why I just wanted to like take some time and go into it a little detailed mode. So what we'll do? Okay. Designing S3. We'll start with the brainstorm, right? Bahut maza aayega usme. So let's start with the brainstorm and see like what you should be doing is you should be identifying the patterns. Like what would S3 be? Which database? So we have seen a lot of stuff till date. So which database is it really similar to with respect to design? And what kind of Lego blocks that you can pick from earlier designs and implement and just basically plug and play here and see if it works. Okay, let's start with the brainstorming thing till 4:30. Sure. Who wants to go first?
The distributed key value store that we design, I mean, a multi-level, basically API gateway, and then the storage layer. It looks like that.
Distributed KV store. Distributed key value. We did distributed cache.
Yeah. Sorry, yeah, distributed.
Distributed cache. How is it similar to distributed cache?
I mean, there is a storage layer, there is an API layer, and that's what S3 is about. So
because separate storage and API layer. And anything else? Any other caveat with respect to distributed cache or anything specific that we can do? Like okay, with respect to architecture, we can go with like a separate storage layer and a separate API layer. Anything else? that you can pick and plug here with S3?
The log storage design from the key value store that we did last week.
How come?
Because
Hmm.
the things like the index and the put and the get, those kind of calls, being able to keep them immutable and so be able to recreate that state, things like that would be good to have.
But immutability, how would you leverage immutability here? Like what would you do with that?
It gives the user to go back in time, restore just restore files to a previous state, and and also if there is a replication lag across data centers, it allows you to replay those kind of operations and recreate the state. So storing those operations in log fashion allows you to do all those things.
What else can you get advantage of by using log structured storage? Any other advantage that you see? Apart from it being immutable. So when you're doing immutable, so log structured, once write is done, the write is done. So you will get multiple versions of the same file, which obviously S3 has to support, because you should be able to go back in time and do that. What else with immutability? So will you do like all writes happen as a new entry so that you can pick it? That is one. Anything else with respect to log structured storage that you can read?
SM is basically if you want very high throughput and append only kind of, then generally use
High throughput.
high write throughput.
Yeah, it's efficient for writes, no random seeks.
Do S3
And it
support
is-
random seeks?
Random 6 it would be slow. Yeah.
It is cheap, right?
Cheap. Why
Yeah.
is cheap being that important? Because
Yeah,
S3 humongous scale, right? Because
exactly.
like people are supposed to use S3 as their dumping ground. It is for almost all AWS customers have their data lake on S3. Right, S3 is supposed to be acting as a distributed file system for most of the companies out there. For most of the managed services, S3 becomes that distributed file system or distributed file storage. So that is why the biggest advantage that you get is like it is cheap. The reason it is cheap is something that we discussed last week. So what would happen is if you want high write throughput, you can either use SSD, you can either use spinning disk in append only mode, right? So if you're using SSD, it becomes costly. So at a scale where like people are flocking in zettabytes of data every day, but basically combining all the customers, not just one, but at least petabyte of data every day from 50% of customers is something that would require a massive cluster of disk storages, which means that even a $1 saving in one disk would amount to millions of dollars saved, right? So because like here, when we talk about S3 or when we talk about blob storages, we have to assume or like we have this thing that from day zero, you have to optimize for cost, because if you make a decision like let's use SSD for and we'll see, and people would start dumping in like petabytes of data, right? So SSD would go, so the cost of your S3 would go like humongous. So you have to start thinking about those optimizations. That is where instead of using SSD, another option with very high write throughput, because you have to support high write throughput, log structured storage will help us do that. So something similar to like append only mode, where you are using magnetic disk, which cannot or which would not need to go back again and again unless the read happens. It would not have to go back again and again and then do a disk seek and do that, because you are not supporting random writes. Through that, you are getting a high write throughput out of your spinning disk hard disk, which would help you save the cost. So that is a major decision. Immutability, because we need multiple versions, because like people like even with Google Drive, when you upload the file with the same name, it adds it as a new version. So you would have to go back in time. This also extends to Dropbox. Any cloud storage you see, Dropbox, Google Drive, S3, Azure Blob Storage, anything, wherever you need multiple versions. So this is just that hint. So So the kind of constraints we play with in systems, that would obviously give us some hints. Yeah, you have to use this, you have to use that. Because like if you want to have high write throughput, you have to go with append only, so lock structured. But then through that, you would also get benefit of multi-version systems. Okay, do you need multi-version systems? So then lock structured and all, right? So you can think it from that perspective. So most of the system design part is nothing but Lego blocks. We have covered most of them till now. It's just about like putting and placing them in one place. Okay. The only thing, let's also cover this part. ये भी brainstorm कर लेते, and then we'll go through the formal design, because then it will become very easy. What would be a challenge? Like we have made decision of a system which is very similar to like distributed cache, because we have to have separate storage and API layer, similar to how we discussed with distributed cache. We need lock structured storage that we discussed. What is that? What is the next big challenge for basically while designing S3?
It needs to have high availability. So if it's all within the same data center, it's not in, you need to have it across data centers. And that means things like replication lags, things that will start coming in.
So how will you address this situation?
So we need to be
Replication.
able.
Hello?
Could be.
अच्छा क्या है ना, हाँ ठीक है, मेरा इंटरनेट नहीं, I was just wondering that. Yeah. You need high availability. High availability of the system is okay. High availability of data, it's the major concern of high availability of data. So replicating it across data centers makes sense, but when you do it replication across data center, your replication lag. Why would replication lag become a problem when we are replicating it across data center? How would that become a problem?
I mean, the network is limited between the data
Mhm.
centers, right? The bandwidth is limited, so you will
But then
be.
how would there be a replication? So for an end user, like if you are the end consumer of S3, you write it at one place. Why would you care? Well, you would always read from the place where you have written, right? So how would replica lag would be a concern for end user? It may be a concern for ensuring durability or high availability, but definitely not for end user.
Yeah.
Right. So there is this very fine line to understand. Like this constraint is, so although this looks like a non-functional requirement, but you can think of it from the lens of functional requirement. Like for your end user, it would not matter if, because the end user should never see a replication. Like the user has written a file, he or she should be immediately able to fetch the file and basically perform some operation on that. Replication lag is a concern of yours where you are replicating the data to make it highly available and durable. Right. So what else?
Unique URL for each file.
That is straightforward, no? Because it's the file name and the file path at which user is uploading it. There is no like unique ID generated for each file or something like that.
But if the folder is same for two users and the file is same, then
Bucket is different. Bucket is different. Right?
It's a unique bucket.
Yeah, buckets are different. Na? Have you used S3?
Yes.
Right. So S3 पे we first create a bucket and then उसमें folder structures होते हैं. Right. And a bucket is like for an account. It is not specific to like independent or individual users. Right. If you would want to build something like that, you would create one folder for each user within that bucket and then have as many files as you want there.
Yes.
So there can be clash over the file names, right? If user is not conscious.
But
he will
still
get
here
error.
the developer is at here the primary consumer is developer, so the file would be overwritten. The developer would know that the file already exists. I need to handle that case.
Yeah, he will get an error if he tries to add the same duplicate file name, right?
No, typically it is a replace operation.
So replace. So can't it be like unique identifier attached for each file.
That's the path of the file. But why would you need to have a unique identifier for it? That's still just the path of the file.
I mean, to avoid such errors, maybe just without knowing, it goes and overwrites the file, kind of.
No, but that is not your concern, because like the end consumer of your is a developer, and the developer would have to know that if the file, when you're doing put, it would replace the old content.
No, here it may not be developer, right? It's end user. Somebody is doing using the S3 storage, and he is just uploading the file. He doesn't know what is going underlying, right? And he
No, but
doesn't see
still, so
he
then you would need to have multiple versions of the file. If you're doing a replacement, if you enable multiple versions on that,
Okay.
he or she would be able to track it back,
Okay.
and then basically revert the changes, right?
Okay.
It could be some sort of compression mechanism to be there in the S3 to reduce the size, or some encryption algorithm, like for the security purpose.
Nice encryption and
Compression.
Also, we can like divide the data into multiple chunks and store it. Like instead of storing it to a single blob.
why would you do that? Because when you're reading file, would you want to like have it chunked and then do it?
No, even let's say he is uploading a big file, and let's say
That's upload download optimization.
Yeah.
It's more with respect to how a gigantic file is uploaded, but it is not the concern of storage system where we would store it in chunks. So that's optimization on the upload and download part, but not with the storage.
So even it reaches to, let's say, your app server in while upload in chunks. So even to upload to, let's say, S3 storage server, it's also again a network call, right?
Yes,
So if it's not chunk, if you are trying to upload 1 GB again, say you coalesce all, then it may be time consuming, right? No, let's say it fails in between, then you have to restart again.
yes.
So that way, if it's chunked, then it would be easier to get incremental upload. Even for S3, it can be used.
We need some rate limiting, right?
So rate limiting, agreed.
We need things like CRC checks for if this can fail.
Yes, CRC checks, basically durability, or rather integrity of the data. We will be covering all of this thing by the way. Okay. What else?
And main thing is how do you locate where these files are, because it's a huge scale, right? So locating, partitioning, Yeah.
What would happen when you partition the data? Once you partition the data, you are adding one more problem into your system. What's that?
So these partitioning servers also has to be highly available, right?
That is so. So everything has to be highly available with S3.
Yeah.
But then with partition, you are adding one more problem.
Hotspot may be possible.
Hot partitions.
Yeah.
Hot partitions become the problem.
Yeah.
How can we tackle hot partitions?
Maybe if we are using range based, then as soon as the partition goes size, we split the range. That's one way. We are using range based, or maybe health monitoring we are doing and then doing listening.
Why not consistent hashing?
Consistent hashing can also be used. Yeah, that's another way. Yeah.
I mean, consistent hashing distributes it separates the load, right? But the hot partition, I mean, whatever the data that is hot, even if you partition, even if you add a cluster, it doesn't make a difference. So consistent hashing doesn't solve the problem. At least the way I will do it is, I mean, for the hot data, you have a separate what can I say, in the partition, in the basically consistent hashing. Before doing the consistent hash, just add a premium customers basically, whoever is using too much, make a check for them and have a separate cluster for them.
No, that is that. But even for a customer, when the data is partitioned, there might be a hot partition, which might create a problem.
Yeah, right. Yeah. So maybe consistent hashing may come to the rescue, but there should be proper health monitoring, and then but how will it happen automatically? That's I don't know.
And where would the mappings be stored as to this file is under this disk, this file is under this disk?
That has to be algorithmic, that has to be mathematical, or that has to be some sort of configuration. It basically, it could be one of these three. Like there is no fourth way to do it. Right. So it could be like mapping, this goes there, this goes there, some sort of static.
No. I've stored, let's say I've stored 1 GB of file, and there's one disk allocated to me, right? But where that will be stored in database or database, right? That this user.
So there are so many different kind of challenges here, right? And we will also discuss like consistent hashing, why not, partitioning, how to handle hot partitions, CRC availability, sub. I'm so glad like we were able to cover most of it from like just doing a very tiny brainstorming session. Like great job, guys. Thanks. Chala. We'll now like now the overall design becomes much simpler because like everyone has an overview around what all things we would be covering and basically what kind of pitfalls would we fall into. Right. So we'll start with that. So S3 is nothing but a very simple distributed file storage. In most cases, it is used as data lakes. Like right now, it has given a very tough fight to HDFS, self-managed on-premise sub. Everyone is doing S3 as the data lake. What it does is it's very simple. It's just a folder in the cloud, similar to Google Drive. This design, the one that we'll be discussing, we have just discussed a lot of pitfalls, like what would make a good design, because with system design there is no one right answer. Like you can pick one algorithm over other, you can pick one design pattern over other and still have an equivalently good design, right? So it's important to understand the pitfalls, like because that's where the crunch is. Like that's something that is not intuitive enough. So that's what we'll be trying to build along through this entire design. Okay. So a very simple S3 server that you can build on day one is something that what we did with distributed cache. Like user, API server, use the memory of API server, in this case hard disk of the API server, to store the data. Right. So S3 is nothing but just like one API exposed on top of your file system. By the way, Dropbox on day zero was looking exactly like this. There is this very famous video on Dropbox system design taken at Stanford or MIT on YouTube. And they also like said the same thing. So Dropbox, and even not just Dropbox, but GitHub also. GitHub was just an interface on top of a file system on which all the repositories were stored. It is that simple. So when you do git merge, git pull on GitHub, it does that. It fires that exact command on its file system, and then it basically gets the data. Right. So there is like nothing fancy about it. Everything starts this small with the basic thing that you have in mind. Like that's how it should be, and it is exactly that. So user, API server, and hard disk. Hard disk where there is folder. So let's say each S3 bucket becomes that one folder which is unique, and within that you can have any sort of file structure as and what user needs. So S3 is just like an API exposed on top of that. So when you do get and then you give a path /home/api/abc.txt, it goes to that hard disk, fetches the file information, reads that file, and sends it back to the user. Like as simple as that. This is the base that this is the foundation that we get. But if you see this API server is something like which is nothing but our S3, it would have to get split into multiple components, and then we'll add a lot of like mirch masala into this and make it scalable. So here the core challenges, so get, put, delete are very simple to implement. It's just like normal file system calls that we make. So what would happen is once you start hitting that scale, one server would not be enough to handle the load. Or second case, your disk is becoming burdened because people are uploading a lot of data. So now what you do is you scale the system. So once you do it, let's say your disk was the bottleneck. You add one more disk. Now, how are you attaching disk? It's like normal USB port, external hard disk, the way you attach. Now, just imagine it that way. So you have one server, though USB port, and in both, so pehle you just added one hard disk in one USB port. Now you added another hard disk into another USB port. Like that's actually on premise. That's exactly what happens. There are these clusters of disks which are attached and detached from servers. Like that's exactly what happens behind the scenes. And here, like we are small, we are tiny. We have one laptop, so we just plug it external hard disk into that and try to build SP out of it. So we can just do that, like hard disk one, hard disk two. Like so, disk was a problem. We added one more. Now what would happen is with two disks in place, how do we decide which one goes where? So this is where our hash function comes in. So let's say what we do is whatever the bucket is, we take the bucket. In this case, it becomes like the top level file path, right? So /home/rpith goes to hard disk one, /etc/system goes to hard disk two, for example, right? So user has created their own sets of folders, and depending on where it hashes, it would go to that particular hard disk, right? But now this was like an intermittent solution to our problem, where our hard disk was becoming the bottleneck. We added one more. Now the next part is, does this scale? No, because what would happen is our disk IO for parallel writes might fail. Our disk storage could be limited. There are limited number of USB ports in your machine, so you can't add one more, because let's say you have at max 2. So how would you scale that? Then overall network connection or overall network IO from your user to your API server might become the bottleneck. Then limited number of network IO connections possible on that server can also be the problem, because right now we're just having one server to serve this, and obviously lots of failures, like your DB or your disk can crash, your machine can crash, like so many things could happen. So we'll add one more solution. So what we do is, to mitigate this problem, we have to horizontally scale. So like we added two external hard disks to one API server. What if we add one load balancer, have multiple similar setups like this, right? So you have load balancer, API server 1, API server 2, and both of them have their own sets of couple of hard disks. So hard disk 1, hard disk 2, hard disk 3, hard disk 4, and you have two API servers here and a load balancer. Why shouldn't we do this? What's the problem here?
We can recreate the same things on both as on the same. We can go to, because the load balancing can be round robin or something like that, and we can keep duplicating the data across the hard disk.
So when we are designing this, the main concern becomes the load balancer, because the way or the load balancing algorithm would be the really key. Because if load balancer is doing let's say round robin, right? So it would not identify this particular folder is present in this API server, so the request has to go here, right? Because then the folder might be present in other place, and if it is doing round robin, so sometime it is written in the first API server ka hard disk 1, sometime it is written in hard disk 4, right? It would become really tricky for to locate the stuff. So that's where your load balancing algorithm has to be sticky. You have to make sticky request. It would be configuring like anything that starts with /home/rpith should go to API server 1, and in that API server 1 it would like apply hash function and find out whether it is hard disk 1 or hard disk 2. Similarly, if it gets request for like /home/vishal, it would do that. Okay, this request should go to API server 2. There would find a hash function. It would find it should go to hard disk 4. Right, something similar to that. So it has to be sticky, and this stickiness should not also be on load balancer side. But if we are having some sort of other algorithm which is not working on hash function, so even allocation between API hard disk, API server and hard disk should also be sticky. Now this sticky could be like, if you're applying math function, it would always output in the same value, but either 0 or 1, so wahi pe jayega. But still it has to be deterministic. So for the same set of input, it should always give same output. It has to be deterministic. So this is where like deciding on the load balancer, the load balancing algorithm becomes very tricky. But now if you see the problem, even after adding multiple servers to this, we are still not able to like solve the problem like efficiently. Like we could do much better here. So the request splitting, we should always go with sticky instead of doing like round robin or list connections, like whatever comes out of the box, right? So what do we do? So similar to what we did with distributed cache, right? We are separating out our, if you see here, the problem was servers, hard disk explicitly connected. And now because of this, we have to make things sticky. So instead of having this storage being attached to the core API server serving the request, similar to what we did with distributed cache, we would split the things. We would let API servers work independently or scale independently, and the storage network scale independently. So think of this as a network of hard disk, right? There might be an interfacing layer sitting in between. These are specialized hardwares, like for disk clusters. If you have ever worked or if you have ever get a chance to work on an on-premise infrastructure, or just take a there are a couple of great videos on YouTube that gives you a sneak peek of the data center. You would find like clusters of hard disk, and even there is this YouTube channel called as Tech Burner. The guy reviews like mobile phones and stuff. Very recently, he set up his own office in which he bought like very expensive set of hard disk. Like you can add 10 terabytes of storage, like 10 hard disk to that one machine, and you can attach it over network. You can go through that to find exactly how those configurations happen. So he used it to set up internet and a small server for his office, and that would give you a very nice sneak peek kya hota exactly. But if you want to do it at data center level, you can obviously check AWS's video on data center. So these are like special hardwares on which what they create is they create a network of storage disk, and there is one interfacing layer. So they all are connected to a central switch. The request always comes to this central switch. Now the API server's job would be to connect to this or to pass the request to this central switch, and this would take care ki kahan pe, on which hard disk does my data exactly lie, or does this data exactly lie. It would go there and get the data. If it's a new put, it would find ki which hard disk or which storage node it should go to. It would go to there and store the content, basically do the update. So it would do this. So the API servers that you see are the core API servers that are there to like handle the HTTP request and some business logic. So then whatever the read write operations that needs to be performed would be delegated to the network of hard disk through this layer. So this layer becomes extremely critical here. Right, so this is that this is that central interfacing layer that would mask, or basically that would create an abstraction of storage layer to API layer. Right. So we separate out API servers and hard disk to avoid limitation of one servers. Now our API servers can independently scale, and our data and our storage network can independently scale. Right. So long as the interfacing layer is aware of it. Right. As simple as that. So we just, by creating abstractions, we are able to independently scale the systems. Stickiness of the request, we would have to ensure that request of a certain folder always goes to a certain storage node. Now API servers have become like independent, so any request can go to any API server. So now our load balancer is free to configure or free to use any algorithm that it requires, like least connection, round robin, random, whatever it wants to do it. But the fun part is that the place where the data should reside, it has to be done. So the stickiness is now being delegated out of the load balancer, out of this, and it sits over here. Right. So now this, my API servers can scale independently. My load balancer does not really have to be sticky anywhere. So request can go to any API server. It would forward it to this interfacing layer. Now this interfacing layer has to ensure stickiness. Key, the data should go or is present in which disk. Right. So by just adding one thing, we are able to independently scale a lot of other components. Right. So this is how like slowly we evolve our system. We find bottlenecks. Like this is exactly how we would have designed a critical section sort of thing. So initially we would put our entire code into as a critical section and add blocks and add basically mutexes above and below it. And then we find out कि अरे नहीं पूरा नहीं चाहिए, let's remove the top 2 lines and bottom 2 lines, and then I'd make those two as a critical section. Then we basically try to reduce the scope and then have that part that would actually be a critical section that we have to worry about. Like this is very similar to this. So we are slowly evolving our system where we found that, okay, now this is not scaling. Let's add more thing. When we added this became the bottleneck. Now let's move our stickiness to the server node, because that's exactly where we need our stickiness to be. Like, because our load balancers need not be sticky, our API servers need not be sticky. What needs to be sticky is our storage layer. So let only that become the sticky part in our entire component, in our entire system. Okay. So now API and storage can scale independently. That's the great way to like design. Now, what comes at that interfacing layer? Like, so that interfacing layer needs to find which hard disk contains which folder. So the most basic solution that would come to like anyone's mind, because like we have learned so many things about math functions and load balancers and all, is like have a hash function. Do a function of p mod n, where p is like path and all. So function at path mod n, it could do that. But what if n changes? The entire data have to be re-indexed, like similar to what we saw with last week when with distributed cache. So same set of problems would come in. If n changes, data has to be migrated. Then obviously the solution to that was consistent hashing at that time when we saw the only minimal data transfer. So something similar we can do here. Then another approach is if we not want to have a hash function to do this, given all the disadvantages, we might have to have static binding, which says that folder 1 is present in this hard disk. Folder 2 is present in this hard disk. So what we need is, we need one metadata database or one meta DB whose job is to hold this information. Once it holds this information, it would make, the request would have to go there. It would fetch from the DB ki kahan pe jana hai. It would go to that disk and then perform that operation. Right. So entries against folder would, and then what if we, one node is deleted? So only that particular node ki bindings needs to be updated. So seems like a better approach than this, but can we do something around that? Ambrish, just give me 1 minute. I'll just cover this and then we'll take questions. Third thing is obviously what we discussed last week was like consistent hashing. Leanest, most efficient. It seems like we can work with that, because like that's exactly what solved problem for us when we were discussing about distributed caches. So can we not directly use that? So it would gracefully handle additions, removal of storage node with minimal data transfer, and boot up and tear down, copying existing data into it. Like all of the things that we discussed with distributed cache is something that we can very well do here. It seems to solve all the problems except one, hard partitions. Right, we'll come to that. So the final thing that I'll cover before we move to let me take some question and then we'll move into stock consistency part. Yeah, Amrish, you had a question.
Actually, I have some questions related to consistent hashing. Theoretically, I know things. Let's say I have 10 nodes and I added one more node, right? So typically what happens, whatever is the range assigned to it, some parts of each node will be shifted to this new one, right? So let's say 1 to 10, 10 to 20. So maybe I add 1 to 10th and 20th and something like that. From all will be shifted to new node. But it's some system administrator has to add this, and he has to configure like there will be some automated way to do that. I mean, it takes only these.
We'll go through this, but I've already covered it in the last week. You can go through the recording.
Yeah. Okay.
I've already covered that. I've already mentioned a blog post which I've already written on consistent hashing. Go through that once, and we can discuss it during a one-on-one session.
Okay, sure. Okay, yeah.
Okay. Any other question before we move into consistent hashing part and understand why it is a problem here? Sure. Good. Okay. So when we use consistent hashing for a problem like S3, what would happen is you would typically do like one S3 bucket. You would have a network of hard disks being present in a ring, right? Let's say your hard disk 1, hard disk 2, hard disk 3, hard disk 4 is present here. Your bucket, similar to what we did with distributed cache, got hashed in this location. So it found the rightmost or the first node towards the right of it as the owner of my bucket. So it would go into this hard disk. So all the requests for this bucket would go to this hard disk. So all the hard disk, so with this, what would happen is if the problem of hot partition comes in, right? When a partition becomes hot, if we add one more node, it is still not solving the problem because it is just trying to, it will split the storage space. But even if I add, let's say when my partition would become hot. So it is not basically a partition, but actually a bucket that is becoming hot, right? Because like, let's say from an end user's perspective, the end user is just creating one S3 bucket, right? And that user can choose to write as many things to that S3 bucket as he or she wants. Now, what would happen is the operations that are happening on the entity called bucket. And if we are applying the consistent hashing function or consistent hashing to hash buckets, what would happen is bucket was going to HDD1. Let's say I added another HDD here. Let's say HDD5. Now bucket ka data would start going over here. But what's hot? Hot is bucket. If bucket is hot, if one bucket is getting too many requests, it's just that the requests which were being served from HDD1 are now being served from HDD5. Right? But the hotness, instead of HDD1 becoming hot, now HDD5 is becoming hot. Have we actually solved the problem? No, we just, it's like we sweeping the house. We never eliminate the dust. The dust just gets moved from the house to the dustbin, but it's still there. The kachra is still there. That's what exactly has happened here. You have tried to sweep it. You have tried to solve the problem, but you have just tried to, defer the problem for something. It's still not solving it. So the hotness, so that is exactly where we need to understand what exactly is the problem. So the problem of hot partition is at a bucket level. So we may have to find a different solution to this. So it definitely cannot happen at the bucket side of things, right? But we would come to a solution on how we can extend it to other places. Okay, so now here, when we're talking about hard disk, if you see, this hard disks are like not just mere hard disk, but they are storage disk having a very lightweight HTTP server or maybe a TCP, RPC, or anything raw TCP connection server, and which would act as an interface. So like very teeny tiny server running and some storage associated with it, so that I can connect to that hard disk and make that call sort of stuff. And these are all absolutely, so these are all specialized hardwares that come in that act as this part. So you as a software developers might not even drill into that problem, but these would be an abstraction created for you by the hardware team for that. Okay, so if we were discussing consistent hashing, now a better way to do it to handle hot partition problem would not be consistent hashing, but to use range-based partitioning. So now let's say what we do is, instead of putting it into a ring, because like what happens with consistent hashing, like here is what makes it critical for us to understand what benefit does consistent hashing actually gives us. Although we say it gives us minimal data transfer and all of those fancy stuff, what it is actually doing is it is leveraging randomization. How? Because output of hash functions, we don't know. We don't know where my hash function would hash a certain bucket or a certain hard disk in my ring. Right. So it would typically try to implement, or it would handle the system such that everything is homogeneous enough. Right. It would assume that. And that's where, like, you don't know where it is going to hash. So then how are you even solving the problem? Because like you don't know where it is going to hash. So it is every point on that ring is equally likely to be the output of your hash function given a value. So it could hash at any place. So by adding even more nodes, you're not actually solving the problem. This is specific to this case, right? For storage, for persistent storages, not for like load balancer. For load balancer, it would still work. For distributed cache, it would still work. Right? But for storages at this scale, it might not be the best choice. Okay? It depends on the scale at which we are operating, right? It is not, again, no one right answer, right? So consistent hashing for storage of caches was a good solution. Consistent hashing for storage of persistent data on like S3 is a bad solution, right? So a good solution for a problem like this would be range-based partitioning. Now what we do is, let's say hypothetically, we have a range from A to Z, right? So these are like all the folders or all the buckets that starts with string A to Z, right? So that is there in my one range. So now what do? I create like A to E goes to the first partition, F to H goes to second, I to K goes to third, L to R goes to fourth, S to U goes to fifth, V to Z goes to sixth, right? This way, what I've given is I've explicitly being like statically told that A to E is going in this hard disk only, F to H is going here only, right? So now what advantage would this give us? Like it would be easier for us to identify the hot partition. Let's say my L to R is the hot partition right now. Now, when this is hot partition, it implies that buckets that starts with L and till the bucket that starts with R are the one that is getting too much of traffic. Maybe there is few buckets that starts with M that is creating the problem. So what would we do? We would split the L to R wala partition into L to M and N to R, right? So just adding, so creating that explicitly exclusive partition sets and then basically splitting the problem. So with consistent hashing, it was like random because you don't know where in the ring it would fit. But with range-based partitioning, we are actually doing consistent hashing, but instead of relying it on a hash function, we are explicitly allocating the ranges. Got it? So this ring is nothing but like A, B, C, D, E, F, G, S to Z. Now we have given key A to E goes to this path, F to H goes to this path. Like, so this is a very subtle difference. So consistent hashing and range-based partitioning are actually very similar. It's just that one uses hash function, another uses static thing. Otherwise, the range wala thing is exactly the same. So once we identify, okay, this is my hot partition, I'll add one more entity in between. So I'll define one more hard disk where the data would be there for L to M and N to R. So this way, through this range-based partitioning, what do we get is we make performance isolation easier. So let's say bucket starting with M is creating a little bit of havoc, right? So it is only affecting this. My other hard disks are not getting affected at all. Like they are all very, like all the traffic that goes there, they are very well able to handle it, right? So the performance isolation becomes easier. You can easily pinpoint, okay, this is the bottleneck, let's scale this up, right? So makes performance isolation easier. Each account's object will be stored together, right? So this is another big advantage because like for one account, you can like have like multiple layer of range-based partitioning, like one on the account layer. Within that account, you can have bucket layer and whatnot. So all the buckets, all the objects of a particular bucket or of a particular organization will be sitting together in one partition, or maybe a couple of partitions here and there, but they would be lying very close to each other. So you don't really have to go, like if you do a pure consistent hashing, instead of doing it on bucket size or bucket type, bucket level, what if we do it at a file level? So it might be split at very random places in the hash, string, which is basically not a right way to do it because you cannot like find the hot partitions. You cannot find like what exactly is the problem, right? So let me just reiterate on that. That's a critical point. Okay,
so basically, it for a user or organization, it gives a data locality rather than
yes, basically spatial locality ka reference, matlab, it makes it easier.
Otherwise, scatter gather he has to apply.
Scatter gather here. So what I was talking about is instead of doing it bucket level, what if we do it at file level? So let's say this is a file, right? So this file could belong to any bucket, any organization, anywhere. And then we have some hard disk present across my ring. Now what would happen is my file F1, F2, F3. Now F1 could be belonging to organization 1, F2 belonging to some random organization, F3 belonging to some random bucket, right? So these files are going to present in H1, H2, H3. So this means that on H1, H2, H3, H4, it is not specific that file of only one organization is present. So let's say file F is present for organization 1, it is for organization 2, it is for organization 3, and this F4 is for organization 3, right? So now if you see file for organization 3, which is F4 and F4 and F3, they are present in H1 and H4, right? So there is no one place to find it ki kya hua. So now let's say if H1 is the hot partition right now, let's say H1 is seeing lot of writes happening. Now it could be because of organization 1 or organization 3, right? How would we identify that, right? We cannot penalize them because we don't know what's causing the problem, right? Because like this partition is becoming hotter because of what, right? So if we do a file based consistent hashing here, it's even worse choice to do that, right? Because you would need to have like complete isolation of performance. Like H1 will only be affected by just one organization's data, for example, right? So you would need to have some way through which you would get predictability in the system. If you make a lot of random allocations or random ownerships by doing it at file level and consistent hashing, you are losing on that valuable information. And so that is where you would have to find a way, you would have to find a middle ground. So that is exactly where range-based partitioning comes into the picture. Just give me 2 minutes, Amrish. We'll take questions for about that. Okay. So hash-based approaches typically loses on the locality of objects, right? This is exactly what we saw, because it can hash at any location. It is random. Random with respect to math function, it is although it is deterministic, but you can't know, you won't know where it would fit into the ring, right? So that is where, to gain predictability, to gain throttling, to handle throttling, because now what would happen is, let's say if this was not at file level, if it was like, let's say org level or bucket level, you can easily find, okay, this is what is making this partition hot. Let me throttle the request of this particular client, right? So you can do that. So throttling becomes easier. So where you have like separation of responsibility, separation of ownership, it makes life very, very, very simple for everyone to do it. So that's why range-based partitioning becomes a great choice here. So how to deal with hot nodes if one node is getting a lot of traffic, it makes it hot. So we split it. We split it into two mutually exclusive partitions. So let's say it was L2R. Let me take an example. Let's say this was what kind of L is that? Let's say this L2R, we split it into L2M and N2R. Right. So these are like mutually exclusive partitions. So if my M partition was creating the problem, now this only has to take load from L2M, and now my N2R would be like happy. Nahi aa raha loads out. Right. So with range-based partitioning, this becomes very simple. If the request goes beyond limits of like how much it can handle, you can obviously throttle the request. You can hold the number of requests per account or for each that comes in, and then you can like throttle if needed. Right. Okay. Let me take a couple of questions before we go on a break. The partition manager and all would come in. Yeah, Amrish, you had a question.
So basically, I think it's in the next slide. Answer like
the partition manager.
Yeah.
Who would know with what managers what? Yeah. Okay. Yeah, Sanjay.
I just want to be clear on this file-based consistent hashing. You said with bucket, you said we could not split the bucket, so that is why it is we can have hot partitions.
Yeah.
But with file-based, we can, because files are more atomic. We can add a new node between H1 and H4 and to solve the hot partition. But the problem is spatial
organization level wala thing, because now one partition might become hot, but you cannot attribute it to just one organization or one account being the problem there, because it could be because of O1 or O3. You can't know because of whom it happened. So basically throttling. So what would happen is, if O1 is throwing a lot of requests, right, and now you would have to throttle it on the hard disk level. So because of O1 abusing the system, O3 is also getting affected.
Got it. But then that can exist even for caches, right? Like key value
But then for
this-
caches, it was not across organization. With S3, you can have like so many clients, so many buckets being there. If you're just building S3 for your organizations, you would have like strict SLAs and all, so that mismanagement is not happening. Right? But if you're building something that goes across organizations and across all things, where you would need a pure mutually exclusive tenant-based architectures, you cannot go with a solution like this.
Okay. And for the partition thing, if the node responsible for that partition comes down, like for example, A2E comes down, then does F2H take over the ownership for that? Just like splitting partition, do we?
No. This is not consistent hashing where the ownership would be transferred. We would be handling partition failovers, partition failures after the pay. Yeah, how would we handle that?
Okay.
Yeah, Varun?
I mean, the approach of range-based partitioning looks good, but I mean, how about a hybrid approach? I mean, having a hot filter and then having a random, that feels like a more subtle.
Yeah, but you would miss out on that one part. You would miss out on locality of file. So let's say let's say there is one directory and that directory contains 10 files. If those 10 files are present on 3 or 4 different hard disks versus they are all present on that one hard disk.
Yeah, I think.
Right. That's one thing that would be missing there.
But even in that case, if you are partitioning on the account, I mean, if you are doing a consistent hash on the account, then it will hit the same partition, right?
Yes. Yes.
I mean,
Again,
in that
basically
case,
that's what happens with system design. So again, no one right answer. See, every approach would have some pros and some cons. You would have to make adjustments like, okay, I want this. So for me, this is so for me, feature A is a priority and feature B can take a hit. For some use case, feature B could be the priority, feature A can take a hit. Okay. Any other question? Or if not, we can quickly take a break and then continue the discussion. No? Okay, chalo. Let's catch up at 5:20. We'll go through partition managers and then handle availability, durability of data, and see different components that would come together to solve this problem. And then second design that we'll be covering will be LSM trees. So that's when our high throughput systems would kick in. So high throughput storage engines is what we would be targeting today. Okay. Chalo. See you at 5:20. Thanks. let's start with partition manager. So now that we have, so many partitions in the picture, and we'd have to just scale it, what we need is like someone to manage it. Like obviously we need to know, but we were discussing about hot partitions, that how would we know that a partition is hot, right? So, and who owns what? Like there has to be some place where we are mapping okay, this partition is what was responsible. Like if we are splitting it like this, we need to know that basically someone needs to know that the partition was responsible for L to R wali range, but now it is being split into two partitions. So one more partition is added. First is responsible for L to M, and second one is responsible for N to R. Like who will hold this information? So this information will be held by a partition manager. Right. So now this partition manager could be a normal server that is serving basic HTTP request about this information, like whoever needs that, and is storing this information into a distributed storage like Zookeeper. Like anything would do here. If you can rely, you can also rely on DynamoDB to do that, because all you seek is distributed and atomic operations to like do it quickly. Like that's all you need. So you can use anything that give you any database or any storage engine that would give you those functionalities, right? So the job of partition manager would be to keep track of and splitting big object tables into range partitions and assigning each partition to a partition server to serve and access those objects. So basically what would happen is like every API server, like now your API server comes to the API server would have to reach out to a place. Let's say it would reach out to a partition manager and would say, so let's say your user made a request, give me a file this from this bucket. Now, where would this request forward to? So this request came to a API server. Now this request would be forwarded to a partition manager. So this partition manager is nothing but that interfacing layer that we were talking about, that abstracts the entire partitions for you. That would be your partition manager. So the request would come to a partition manager, and then either your partition manager can serve the request or either you can do it. That's the different game. But still, your API server can talk to partition manager, and from that partition manager, you would get that information that which partition holds the data, and then it would go to that partition and make a call and get the data, right? And partition manager would also ensure that only one partition server owns an actual partition, right? So actual partition. So this was the partition server that we talked about, where it had storage layer and API layer. So here, what it also has to ensure is like one physical partition, like one, sorry, not physical partition, one this range is held by just one partition server. Like it should not be the case that L to M are basically two partition servers are responsible for L to M range, right? It should be only one that is responsible, because the writes and the reads will all go to this one place. There is no like master replica setup, right? All the writes, all the reads of a partition would always go to this one node. So that's why what it would have to do is like one partition server, or rather one partition key ownership is with one partition server, but one partition server can hold ownership of multiple partitions. So like, for example, one partition server can hold information about L to M and some other partition, right? So you can multiplex multiple partitions onto one partition server, but one partition, which is L to M, should only be part of one partition server, right? So this way we can leverage we can use our resources very efficiently. Yeah. Now, how will our partition manager know which server owns which ranged partition, right? So this is where it would need table, like something I was discussing, like it can use Zookeeper to hold that information, like some place where it would store that partition map table, right? So you would have a partition manager which is talking to multiple partition servers, and it would have this information stored, that this range is with this partition. Where it would store it in this partition map table. Now this partition map table will have only this information, nothing else, right? It stores the split details of n ranged partitions and assignment to partition servers into partition table with very simple terms like L to R present in this server, M to N present in this server, and so on and so forth, right? Something like that. It would be stored in partition map table. Now, how would a partition server know which partitions they own? Because like up till now, the partition manager knows, right? But then how would your partition server know ki that is responsible for which, right? So then it would talk to partition manager because partition manager has that information. So now when someone is trying to, okay, let me do that. So here, few distributed system jargons would come in. So here what is there is you have one partition manager who is responsible for managing all the partition servers that we have. We have partition map table who that contains the information that this range partition is owned by this partition server, right? Now what would happen is now this partition server also needs to know that I own this range, right? So now this partition server would have to have the data and the APIs to need to have access to that thing, right? So then it should know that it is responsible to take rights of this. So now this would use some lock service that would help it acquire a lock. For example, now comes to the part where why would we need a lock service? Like it can just ask partition manager to do it, but basically the partition manager will talk to lock service to ensure that one range partition is not allocated to multiple partition servers, right? So let's say one partition is vacant, like let's say partition L2R, no one owns it. Now what would happen is all the partition server will trigger an election algorithm which would say ki, Arey, I want to own this partition, but then there should be just one partition server that should get that ownership, right? This is exactly where lock service comes into the picture, whose job would be to to ensure that only one owns it. Now this is an implementation taken from Azure's paper, but if you do it now, obviously there is no one right way to design it, right? You can also do this, that let partition manager take that call, let partition manager decide who owns it, and then let partition server, and then it informing partition server key I am doing it. Like let's say a very trivial design like someone like we would do is something that all partition server can call this partition map table and see which one I own. Like that could be another way to design it, right? This approach is taken from Azure's paper, so they took up this choice. So just to add this sort of stuff where all the theory of distributed systems that we read, like where have we used it, this is something that Azure uses it in production, right? So I just thought of like adding it into here. But if I were to do it like on day zero, I would still let my partition server ping partition map table to get the data, which one I own, right? And which partition partition server owns, and for partition server, like which partitions I own, and it would get that information and then access that data, right? But the approach that Azure people went with is like partition servers were being smart enough to identify that this partition is empty, so whoever wants to own it can own it. So that's what partition manager would say, okay, let's say one of the partition server went down that was responsible for like a couple of partitions. So partition manager would then okay, one more thing, leader election. So this partition manager is not just one machine, by the way. Partition manager is also a set of machines, out of which one is the master, all others are a replica sort of stuff, right? So right, so that who is the master is also decided by that lock service, so that runs Paxos. So leader election algorithms kicks in there as well. Second one, where leader election kicks in, where you can make a partition manager smart enough or your partition server smart enough to identify that this partition is vacant, so I would run for an election for that, right? So I would want to own that, right? This was approach that was used long back but was deprecated, but that is another approach to do it. Third is your partition servers directly talking to partition map table to get their data, right? So partition map, if they have access to partition map table, they can do it, or they can go do it via partition manager, but somehow they would have to be notified for that. Now the partition servers also uses log service to keep state about logs and assignments. So assignments of file objects, assignments of like let's say two processes or two people trying to update the same file. So it has to be like one process trying to update the file, another one is also trying to update the file, then some sort of locking and all. This is where this lock service comes in. So it plays a very central part into doing leader election for partition manager, allowing assignments for the partition servers, letting partition servers store the locks ka data for like this file object is being consumed by this and is logged by this. Maybe some sort of conditional puts for that lock service would come into the picture. Okay. Yeah, Amrish.
So here, in case of partition manager, rather than partition servers themselves go for what I should get assigned, partition manager should decide.
There are two ways to do it. It's there in the paper. So they have specified that they first, so they try to implement. They actually adjust paper. They reference another paper where they said that the first implementation was that partition server were trying to say, I can. So basically, partition manager and partition server used to run a gossip protocol. Partition manager would spread out, okay, this partition is right now unallocated. Who can own it? So they first tried to make partition servers smart enough. So when partition servers were made smart enough, so they used to run in elections. Okay, I can own it, I can own it, I can own it. And then they used to run an election algorithm. But then what Azure guys did was they implemented this on partition manager. So they said, let partition manager handle everything. Partition manager would actually do the part where it would identify this partition is khali, and it would decide which partition server would own it directly, and not let partition server take that call. So that is where we would need another component that would measure the health of a partition server, okay, how healthy it is or how much load it has, and so that partition manager take that call.
Yeah, so basically these partition servers data would be replicated to other.
Would be replicated.
I thought the another leader election would be who would be the leader of those replicas.
वो आएगा data वाला आगे कि जहाँ पे right now data is with this, we'll be splitting this layer into two layers where the storage would be made separate and basically abstracted. So just evolving the system step by step.
Okay, so here let's say partition servers are there, and because we are having this some kind of configuration service, and one goes down, partition manager will come to know. So if any moment of time, if it goes down, so it will be some replica will become leader of that partition.
Yes, yes.
Right. So in case user wants to add, not user, if it has to, partition servers has to be increased, only way is to go to a configuration service and add it, right? Yes. Are there any other mechanism?
No.
Okay. So actually I had faced this, so I am asking.
Yeah, it would have to go through configuration service.
Okay, yeah.
Because basically that is the source of truth. That knows everything.
Yeah. So other ways, some gossip membership protocol to detect.
That's not that reliable as compared to going to a central place and then getting that information.
Yeah, that's what I read somewhere. Uber's this ring pop thing.
Yeah, ring pop.
Yeah, so there they say that all these they use gossip internally to detect this, but they said it doesn't scale after certain number of nodes, something like that.
Yeah, gossip protocol won't, because it will basically flood the network to do that, to basically to do that gossip. Okay. So that is not scalable, and it takes quite a bit of time to basically come to a consensus.
Yeah, around 1,000 nodes, it takes around 10 minutes or something like that. Yeah.
So when you're building a very highly available system, you can't wait for that much of time.
Yeah, right.
That is exactly why most of these things are now offloaded to managed databases, whose job, like for example, using a database like DynamoDB or MySQL or Zookeeper to hold this kind of information, that would help you basically avoid doing gossips. So if you see lately, a lot of gossip protocols, although people say that they use it, but it's a very old architecture. Now people are not relying a lot on gossip protocols.
Yeah, I remember somewhere they open sourced this ring pop, and then Uber guys themselves said that we won't be using this.
Yeah.
Yeah.
That always happens. Okay. So the flow for now would be like from the partition service, when API wants some information, data or object, it talks to your partition map table. So like first thing, your API got the request, it would get the partition from the partition map table, and then your API server can, do the read write on the partition server directly. Right. So other way would be like your partition, it's just this partition map table is just a pure database. So API server would go to this, get the data, and then talk to partition server. So here another approach was let API server talk to partition manager, and then partition manager getting the data from partition map table. Azure paper, so this entire thing is taken from Azure's blob storage research paper. So they chose to like let API server directly talk to partition map table because like schema doesn't change a lot. So API servers are directly talking to partition map table to get the partition versus going through a partition manager and adding one more hop there, because this has to happen for every single API request. So it would help us save quite a bit of time there. Okay. So now what would happen when a partition server goes down? The partitions owned by that partition server is now reassigned to other partition servers. Now this is done by the partition manager and it updates the partition map table. So now my partition manager found out that this partition server is not healthy and it died off. So it would see that, okay, these partitions were assigned to this partition server, which is now orphaned. So now I would have to assign it to different partitions. So now this, it would change the partition map table and would just change the entry. That is it. So now partition server, now your partition server starts serving the newly assigned partitions as per lease from the lock server. So go locking protocol and all would come into the picture and it would do that. So when your partition server, partition manager found that one partition server went down, it would update the partition map table. The partitions that were owned by this partition server has now to be allocated to this partition server, for example. Right. So now all the requests for that unassigned partition would come over here. Now here, the problem, right, where we now if you see the problem, our partition server was also storing the data, which means if my partition server goes down, if my partition service goes down, if my partition server goes down, I would have to, somehow migrate the data. But if that machine crashed, my data is lost. I cannot do migration if my machine crashed, my hard disk crashed, or something bad happened. Right? So that is typically not a great idea. So that is another place where we would have to separate this thing out into two things. So your partition server would now have to split into two components, where one is just lean and fast, normal TCP based server, and another is storage node. So we just split this thing into a lean and fast partition server and a storage node, which is an abstracted storage layer. So advantage is like partition server going down requires a change in just partition map table, because now your partition server is just this component, right? And storage is yet again abstracted, right? Even from this partition, it is abstracted. So the request, now when the requests are, or when the partition map table is changed with the new mapping, it would just have to update this. Okay, now for this partition, this is responsible. Now it is up to this partition server to somehow communicate to the storage node and solve that problem. So they've just split these two things. Now this is not as abstraction split as we talked about in the previous slides. It is a very small split. I'll explain what exactly happens. So with this sort of approach, just changing that mapping was like solving the problem, right? Because request was going to that partition server 3, which went down, so it was changed to 2 and it started serving faster, lean and fast server. Now what would change? So what did we do is partition server earlier used to get data from the hard disk attached. Now it gets data from a separate abstracted storage layer. Right. Now what we talk about is this storage layer. Exactly what happens behind the scenes. So partition server means we split the server and storage node. Now what exactly is this storage? So now this storage is nothing but it exposes file system like APIs. Right. So your partition server, which is like a very lightweight server, it would talk to this storage over network with a very simple file system like APIs, like open, read, append, update, voila, jo APIs, the file system calls that way. And it allows partition layer to open, close, delete, rename, read, append, and concatenate large files. Like that's exactly what it does. Nothing more. It just a normal server which exposes not HTTP or TCP, just exposes over network on TCP but it just exposes like file system, basically file system like interface calls for partition server to consume. That's what it does. So, okay, we would, so now that we're talking about this storage, now what kind of storage would we use? As we discussed during the brainstorming, we would use like the cheapest one possible. So to keep cloud storage cheap, we'll use like spinning disk, magnetic disk. Tape is something that we can do. That's what S3 uses to store like Glacier like data and all, like usse bhi purana data they would want to store. But tapes are still used. Magnetic spinning disks are very heavily used. So the flash storage is costly. So that's what we use this. Storage layer has one storage layer. Now this is like physical thing. So now this storage layer is nothing but it has multiple physical storage nodes. Right. So these are like, assume that SN5 is like one that this use hard disk, which is added in this rack of system disks. And each node is 10 to terabyte of storage. And there are 20 to 30 such nodes in one layer. So this is one storage layer. So each node is basically 10 to 20 terabytes big. And there are 20 to 30 nodes like this. Like these are physical hard disks which are stored there. Right. Now what would happen is, since we are using spinning disk storages, we would not want to spend time doing disk seeks during writes. So, which means we cannot do random writes, which means to get throughput, we would always have to do append only writes. So every single operation like file create, file update, file delete, every single thing has to be an append only operation. Right? That is something that we have to do. So a delete, so something that we discussed like previous weeks, right? So a create and append is create and update is simple. Delete we'll do soft delete and then merge and compaction and stuff. Right. So what would happen in actual physical layer plus sim linking wala part, right? That would come into the picture. So now what would happen is the write always happens on the head node. Now this head node right now is SN5. Okay, so there were like 20 to 30 nodes in this thing. These are physical storage, but where the write happens could be a sim link, right? So now this sim link is now pointing, it will always write to the head of whatever is there in the list. In the list, the head is SN5 right now. So write happens on the head of the list of which is basically the storage, which is SN5. It writes in the append only mode. Once the node reaches 70% of its capacity. So let's say if it is a 10 terabyte storage long. So once 7 terabytes is filled, it would make SN5 immutable, and it would logically add one new one to the head, which means physically it had SN1 to SN30. Up till now it was writing to SN5. Now it would logically add SN6 at the top. Now when the write call would happen from the partition server on this node, the writes would happen through a file system like interface on a sim link. So it would go through SN6. This way, combination of physical, so physically all 30 servers are, or physically all 30 hard disks are present, but logically there might be just 5, and once 5 is filled, the 6th one is added. Right? It is added at the head of the list. So now the writes start going to the head of the list. Right? So this is handled. So logically adding a new one to the head is handled by the storage layer. You may add one more component to it, like storage manager, who basically does keep, basically there has to be some process or someone who is keeping an eye. My storage node is 70% fill. Now what do I have to do? Once my storage node is 70% fill, I have to add one more storage node at the top of this. Right? So it would logically add one more to that. So we'll add one more component, which is storage manager, whose job is to like keep an eye on this and add one to the head of it. Right? Now, how do we free up space? Log structured storages. We had immutable files. These are immutable disks. What we do is we run merge and compaction on immutable storage nodes. That's it. So because since it is append only, every update is also creating a new file. What if we don't want old files? We can just merge and compact and delete the old data and then reuse the data. Basically put it in the basically keep the disk defragmented and use it. Right. So this is exactly how storage layer functions. Now, a very stupid question, but like, do we need to have a database that holds meta information of a file, of all the files? Like, let's say I have an S3 bucket, and that S3 bucket has, let's say, 100,000 files. Do I need to have a database that holds all the meta information of the file? I said yes, but why? Why or why not?
For read queries and things like that, that you need to.
For read queries about meta information, like what all files are created. I want to serve that interface, right? When was this file last updated? Who holds the permissions to this file? Like all of those information. So typically you can do ls on the partition server and get the data, right? Because your storage layer would also expose similar things. So here what we would, but still it is not best way to do it. Let's have another database, because you would also need to store like who owns this file. Does this file have an expiry? If it has life cycle hooks and whatnot. So we would still need to have a database. You can use MySQL, DynamoDB, any database, but it has to be sharded, because like information of a certain, and you can shard it by bucket, because all the files of a bucket has to be like linearly accessible on the interface. So you would be storing it into, you can shard it by bucket, bucket ID, bucket name and stuff. And you would have to have sharded database for this. So we need to access meta information of file. Last modified at file size is public, who has what access and stuff. We need to define granular access to each file. That information needs to be stored somewhere, right? So we need one metadatabase to hold this kind of information. Okay. Yeah, Amrish?
So partition server itself will act as a metadata server, right?
No, we'll need one more, because partition server, because this is one more layer of abstraction, because for an end user it is just S3 bucket and all the files there. Partition server has access to the actual raw data through storage layer, right? But partition server there is no storage, there is no database to that. You can't apply ls, because see, partition server has access to the storage layer. Your API server is making call to partition server. Partition server is then making file system like calls to storage layer.
Okay.
Right. Now, if I as an user, if I want to know like what all files are there in my S3 bucket, where would I get that information from?
Then it has to scan through and all.
Exactly. That is very costly.
Yeah.
Right. Number one. Plus, you might need to have like granular access to files. Like this file is made public. This file is private but accessible to this account. Right. Those parts. That information has to be stored somewhere.
So how will user get directed to this metadata thing?
API server would then connect to. So like here, good question, by the way. I should have covered that. Wait, I'll show you where exactly it would do that. हाँ, यहाँ पे नहीं. Here, when the information comes to the core API server, this server where the information comes, right now, when we are doing read and write, it is talking to this partition map table. You would have another database here. Jahan pe request comes in for all the meta information, which is like listing of S3 bucket, listing of file information, get file info, not file data, but file info, get file permissions, create digital signatures, like all of those parts. Right. So depending on the API. So if the API comes in which says /read a file, it would go over here, get the partition, and then go to the partition table and then go to partition server and then get the data. Okay. Right. But if it's a list call, it would have to list an S3 bucket. Okay. It would go over here and use this database.
So whenever write comes,
it might check this database.
So metadata will also be updated and storage will happen through partition.
Yes. Okay.
So any metadata information, it will simply direct it to this first.
Yes, exactly. This is exactly where the database would come in. So we would need a database to, to quickly serve that information, because we can't wait for the system to, serve that part.
So this DB also needs to be partition because it's,
partition sharded, yeah.
yeah.
And
Okay.
that would be sharded by bucket name.
Okay. Yeah. Right.
Sure.
The index for the log that will be persisted on disk on the same storage
Index
folder.
for the log as in which one?
Like we discussed last week, that index layer for the file offset to the log.
No. यहाँ पे we would not need those. अच्छा, okay, that is something that is handled by the storage layer. So that is abstracted. That would be handled by storage layer.
Okay.
मतलब the way it would need to handle. So typically having an in-memory index might not be a great choice here, but I did not find an implementation of it. But if we were to implement, since it is append only, there has to be some place through which it would find out that on this hard disk, this is where the file is. It would need that information somewhere. Maybe on disk, maybe in memory. Not sure about it, but it would be there for sure.
Okay.
Okay. Now comes the next part, which is about durability. So S3, the durability is the most important part of S3, just because like it is playing with the data. You cannot lose.
So Arpit, just one question. So how does a partition server detect these many are the storage nodes where I have to write? I mean,
No.
that-
Partition manage. So not partition. So which partition server, right?
yeah, partition server.
So partition server will always write to the head of the list.
So
Then
there
there is
is a dedicated pool of storage nodes.
Yes.
And there,
yeah. Basically, there is a. So these are my storage nodes, right? My partition server is always writing. My partition server is always writing to the head of the list here.
So this is some way. How will it detect that these are there? Are it? Well,
it will be configured. It will be configured at a place. Like my partition server would have this configuration where which storage layer is it connected to.
Okay.
This will be the physical connection.
Okay.
So this will be connection over network. So my partition server. So these are like two very close coupled. So like on this one rack, you have 30 nodes and one partition server.
Oh, it's one-to-one mapping kind of.
One-to-one mapping.
Okay.
Now comes durability wala part, because like durability. Yeah, Bhupendra. Let me just quickly take this question.
Arpit, can you just like repeat? So let's just say at the end of the day, I need to save a.doc file. So I saved it. How after saving it, when I modified it, and then a.doc is again saved, how would the file system or like the last storage layer would ensure it's append only? Like, what is the place that will like put those restrictions?
No, because see, the storage layer has not even exposed the APIs through which you can do disk seeks and updates. It has only allowed you to write it in append only mode.
Okay. So I don't have much experience with like any file system type of APIs. So let's just
when you make a system call called open, usme you pass in the you actually pass in the file mode, which is read,
correct.
read, write, and append. Just think about it that you have opened it in append mode. As simple as that.
Okay.
Right. Instead of just doing it at file level, assume that you are doing it at file system level. Just search for log structured file systems. Just Google log structured file systems. I can definitely explain that, but that's your seed point from which you can start exploring that part. So those restrictions are placed in the whenever a file system, like for example ext3, ntfs, like all of this, whenever you have hard disk, you have some sort of file system implanted in it, right? Now this file system exposes Unix like interface, like open, close, delete, all of these operations, but the code on how to implement it is written with the implementation of this file system ka code.
Correct.
Right. Now the way that code is implemented, that would handle the append only part of it.
Okay.
That would never, even if you write it, it would basically write it at that part. It would never do a disk seek and then write it.
So let's just say the storage the layer won't have those low level implementation at all. Like
it would have that, otherwise you can't add it here.
Like I mean that like writing at a different location, it will have like one implementation that is append.
Append.
That's all. Okay. Good, thanks.
Yeah. So basically think of it like just like ext2, ext3, ext4 like file system is there. You are creating one more file system which is for append only file system.
Okay.
Right. Just my
Got it.
implementation you have not written to do a disk C. Basically that code is commented. Think of it like that.
So here, let's say somebody writes file X and he has written to first head SN5. So when he comes for read after some time, so in the partition server, it will be knowing that at this
Yes.
offset in SN5, I have to look.
It is look. So reads के लिए seeks are allowed.
Okay.
Writes के लिए seeks are not allowed.
Okay. Okay. Yeah. Okay.
चलो.
Thanks.
S3 भी मजा आता है. इतना detailed discussion होता है. Thanks for that. चलो. How do we ensure durability? Like durability is super important because durability pay if your file system, like if your distributed file system is not durable, what would happen? Data loss is not acceptable because like you are deleting client's data. So like that becomes problem. If one of your storage layer goes down, that is a problem. Like you cannot lose data. So how will you ensure durability? So typically one way to ensure durability that would like pan out failures and all would be through storage or through duplication of data. That's the easiest way to do it. Like duplicate the data, add a layer of replication. So you have a storage, write happens on one node, and then you are replicating it somewhere, right? You are replicating it somewhere so that each storage node has a backup. You cannot just have one copy of the data. You always need to have at least two copies of your data, right? So that's how you would save you do ensure durability. But now comes in the part where how would you replicate? There are two modes of replication. One is synchronous replication, another is asynchronous replication. The answer is not binary. You don't have to pick like one over other, right? What you would do is what they have specified, like they do is, and obviously that makes sense. So they have, whenever a write happens, they do one synchronous write within that rack, right? So let's say within the data center, they are doing one synchronous write. So once write came to the storage node, when this write happens, it would make another write into a parallel rack, right? And then it would do an asynchronous write across region into a different data center, maybe a different data center, maybe a cross region or a cross data center, depending on what it is configured. So having at least 3 copies of data, one on the primary storage node, one asynchronous write onto a parallel storage node in the same data center, and third is another an asynchronous write going over the network to either a different data center or to a different region, depending on what you have configured. So this is how you should be ensuring durability. So let's say if your one storage node or one storage rack got burnt, you'd still have another copy of data within the same data center. If your entire data center went underwater, you would have a copy at different data center, right? And if your data is even that critical, so if one continent goes underwater, you would have to have another copy with another continent. Okay, that would be like cross-continent replication, like something similar to that. Okay, so depending on the criticality of data, you would do something like that. But something that comes out of the box is why each copy of your data or each data is copied 3 times. One is the primary storage. Second, another storage in the same data center. Third, across region. So now this region could be as small as different data center in the same region. Like for example, AWS AP Southeast 1 is Singapore region. So Singapore में ही दूसरे data center. So AP Southeast 1A and 1B. So in replicating it in 1B, for example, right? Something similar. So that's how you would be configuring replica. So some synchronous and some asynchronous to ensure durability. Now, how would like, yeah, and also there is one more place of doing replication is using RAID formats. So RAID 0, RAID 1, RAID 5, RAID 10, like each within that disk, a disk can have the RAID configured, something that you might have studied in your database course, that thing. So within that disk, let's say you have a 1 terabyte big hard disk. So you can effectively use 512 GB of it, and other 512 GB of it will be like copy of the data. So even if one local hard disk partition gets corrupt, you can get the request from other thing. And obviously read amplification also happens. So that's RAID 0. And then there are RAID 1, RAID 5, RAID 10. So they read about them. 0, 1, 5, 10, these 4 are very common. Should be having information about, like, कैसा होता है वो, ठीक है? So yeah, some synchronous, some asynchronous within data center across region. It's easier said than done. Implementing it would be mighty tough. For me, it's very easy to like say कि ऐसा कर देंगे. But I know it would be really tough to do that. Okay. So when one region is cut off, a copy of data should be replicated across multiple availability zone, and that has to be asynchronous. Should this be synchronous? No, that should be asynchronous. Otherwise, your main write times would go very high, because synchronous write is not done until the entire write is done, like writing to primary and another secondary storage and all. Tab tak the main write is not done, so that could have an impact. So when you are replicating it through it, do we want to have complete copy of the data? Can we do better? Read about RAID 5 and parity bits. So there are error checking codes and error correcting codes. So in most cases, we just find out like error detecting codes, like we identify that if there is an error, but there are error correcting codes as well that would help us, like if there is a data corruption, it would also help us correct the data. So there are error checking codes and error correcting. I actually forgot the formal name of it, but basically error detecting code and error correcting code. So checksum CRC just helps us identify if there is any issue or not, something that we discussed last week about CRCs. But there are error correcting codes. If there are like few bits changed due to any reason, it would help us correct that part. So that's error correcting code. Now, apart from data durability, we have to ensure data consistency. Data integrity. So when you talk about data integrity, it's like end-to-end checksum. So if we see the way our data is being transferred through so many layers, we cannot have a write which is successful but with incorrect data. Let's say you wrote Arpit. Now Arpit, when it reached your API server, was Arpit. When it read to partition server, it was Arpit. When it wrote to data primary storage, it was Arpit. But when it was replicated to another part, few bits got changed in the middle, and then it wrote ARPIZ, Arpiz kar diya. Right. So now you have written a data which is incorrect. Like this should never happen. When we think about this should never happen, so how can we ensure that we are not writing incorrect data? This is where checksums come into the picture, because error detecting codes. So what we do is at every step, we are always checking the checksums that if my data integrity is correct or not. If it is not correct, I would not accept that. Right. So ensure that corrupted data is not committed in the file system. So at each layer, this checksums are being checked always. So checksum checks while storing, processing, and fetching. So even when you even when you write, read, or process the data, replicate it across systems, every single time you do that checksum check, because data is the biggest asset. And final thing. One final thing about policy management. S3 also, like every file you can have like granular access, like this account has access to this file, this user has access to this file is public and all. Like these sort of accesses are there. We discussed about metadata database that we need. So there has to have rules which are configured on the database. For each file, what's the set of rules? So what would you do is the way you would be designing is to not have rules per object. Right? You can have like by default, all the objects of my bucket is let's say private. I just want to make /a/b/c/d is public. Right. So instead of having one copy of rule per object, right, and you would have like just rules that are configured, and when you get read or write access, you would go through the rules one by one and see which one fits in. Right. A good way to design the database. So should we have one table that holds and tracks rules for all objects uploaded? Definitely no. Depending on what kind of system you have or what kind of rules have you configured. That's why AWS has access policies attached. So you can add as many policies as you want, and it would go in sequence of that. And then you can like configure, okay, this is what the policy is. If this is not successful, if this does not meet the criteria, it would go to the next one. So the first one that meets the criteria, it would apply that. right? Something like that. You can have something similar design with your database. And that's how you'll design policy management on that. All of this thing is taken from paper like Windows Azure Storage. This is the name of the paper, Windows Azure Storage, a highly available cloud storage service with strong consistency. Or definitely I've not covered most, I've tried to cover a lot of it, but I've not covered a lot of intricate details of it, but it would have obviously given you a very high level overview on the kind of challenges that pop in when we're designing a system like this. One paper that I would definitely want you guys to read is Building a Data Store on S3. It's a very small, tiny, fun read, but something that we discussed like last week and today, we saw that how we are leveraging S3 to build us database, like starting from word dictionary to storage engines that we build. Read this database. It's a very fun read, Building a Database on S3. Any questions around S3?
It isn't. Amazon has never written a paper on S3 design.
Amazon is closed source. Amazon to Baba. They have
Yeah,
never,
but
they are open source like some really stupid things. Not good stuff.
DynamoDB, there was a very good paper. But,
Yeah. Because that has, see, they have just published one thing and which has revolutionized the entire space, the entire spectrum of database. Unfortunately, there is no paper on S3 which is out. Not even a white paper helping us understand the basic things about it.
But DynamoDB paper is too much hyped actually, in comparison to this one, Azure's paper. Azure's nobody reads, but it covers a whole lot of information.
Yeah, it does. When I was going through it, I read it 6 times, just understand, because after we reach a certain point and then it clicks, array, this was something that was explained before. Chalo wapas padhte. It was like really fun. They wrote it in such a nice detail. Like if you take time and read through it end to end, you would any day build an S3 of yours. It's really simple then. But
Yeah, it's
they have explained it in very high detail.
I think everybody knows about DynamoDB paper and just reads that. And
yeah,
this
but then people are just picking up like 2 to 3 concepts out of it, and not the entire thing. But yeah, it still gives you a nice overview key, because those guys were the first one to promote it. Like how do we use consistent hashing, and that's what has made like ring-based consistent hashing so famous.
But this one looks to me underrated. This Azure paper.
This is underrated.
That gives hell lot of information.
It does. It was like बहुत मजा आता, मेरे को तो पढ़ के बहुत मजा आया था.
Yeah.
चलो, S3 finally done. Wanted to cover one more. You guys up for it, or can we continue tomorrow? If this was too overwhelming, I can go for an hour or two another. मुझे problem नहीं है. Up to you guys to decide. करे अभी LSM
I'm fine. Please ask others.
चलेगा. ठीक.
My recommendation would be tomorrow. I mean, already बहुत
हो गया ना.
नहीं मतलब हाँ, it can stretch. I mean, this topic can also we might have to leave midway.
नहीं ये पूरा see ऐसा कभी नहीं होगा कि I would not be covering any question. Just that I don't want you guys to be like too exhausted out of this. But S3 का discussion is so interesting कि every step पे there are actually thousands of questions, and a bunch of them are actually counterintuitive. तो बहुत दिमाग दौड़ाना पड़ता है. So up to you. Let's पोल ले सकते क्या Zoom पे? Majority wins करेंगे. अम्बरीश भेज का पुराना था.
We can use reactions, right?
अच्छा reactions. हाँ reactions लेते हैं.
चलो. O means no and thumbs up means yes, sort of.
Chalo. The only person who is so curious to not have it. Vishal is taking a lead. Vishal. Nice. देखो majority जीत जाएगा. Umang is also yes. Prabhat no. Kaustubh no. Chanchal yes. Hands up का क्या है? Yes consider करते हैं इसका. Sanjit yes. Still have more people on yes. ठीक है चलो नहीं let's do it tomorrow. But yeah, don't worry for that. एक भी topic miss नहीं होगा. We would definitely cover every single thing in equal details. That's for sure. I know S3. You guys would believe in the first cohort, S3 was covered last week. मतलब with storage engines final part. मतलब 45 minutes में cover हो गया था because we never went into those details. So that's when in the second one when I realized it was becoming too big, I spilled over S3 to like high throughput systems, and then basically covered everything in detail. The first code with थोड़ा disadvantage was that's why, but वहाँ पे it was like really far too hectic than what you guys are feeling. वहाँ पे तो पूरा storage and all सब was crammed in that 1 week. Chalo, let's in any case let's just continue tomorrow on this high throughput storage engine LSM trees. It's a very short one, but we'll also cover other parts of it around high throughput storage. One good one that I would definitely want to cover is want to introduce DAGs. Airflow, if you guys have not heard of it, Apache Airflow, just Google about it. We'll see where do we use this kind of system and how I have used it, and how we can use it to basically make everything parallel and do things at scale that requires high throughput processing. So we'll cover high throughput storage engine, high throughput processing with that tomorrow. And बाकी अगर कुछ time बच जाता है, I don't know sure बचेगा कि नहीं, but अगर कुछ बच जाता है, we'll take up few questions. Like last cohort में I took up a tiny URL का ID distribution, which is a common topic, but still it opened up quite a bit of eyes ki how it actually happens. And then Dream11 ka storage locking and all with database, something that we already discussed in details, but still if time permits we'll definitely give that a shot. अगर नहीं होता है तो आगे और टाइम मिलेगा नेक्स्ट वीक में, तो तभी भी ले सकते हैं. ठीक है, चलो. Let's conclude for today. If anyone has typically this is done, but if anyone has any questions, I'm opening up the forum for that. If anyone wants to discuss anything, but otherwise feel free to drop. We'll cover high throughput storage tomorrow. Okay, thanks.
Thanks a lot. Yeah.
Arpit, just quick question.
Yeah. Go on, Rob.
Yeah, so if any partition servers go down, you mentioned like a partition server will be having a 2 layers on the storage layer. So if some other partition goes down and there'll be leader election, like how it's handled, like as a partition server will have a 2 storage layers, and like how those design.
No. So when we talk about like partition server going down, so think about it this way. So it will not have 2 storage layers. So one physical server attached to one storage layer. Right. Now this partition server, one physical entity. So basically that also is abstracted. So niche wala layer is also abstracted. But in the paper, what they have mentioned is they have kept it 1-to-1 because they have not seen that high of a failure where the entire rack goes down. So in rack, they typically have, so in real world, the split that happens is the storage layer is just like bunch of hard disk. They have nothing to it. They just have a very close proximity में partition server as that sits on top of it. That's it. They don't really have any connection there apart from a network. Okay. This could be a direct network between a partition server and a hard disk. This is something that they started with, right? But then what they introduced was they created a network out of it. So they created multiple such partition servers and multiple such storage layers, and each partition server was connected to every single storage layer like this. Okay, so this was a network, storage layer ka ek network, partition server ka ek network. Okay, but each partition server was aware of the storage layer. Okay, this way, whenever a partition server ka mapping changes, where it says that now when partition manager server says that this partition server now owns A to B wala partition, for example, then it can directly talk to this abstracted storage layer. So your partition map table would also need to have information ki who holds this and which storage layer to connect to. Maybe some identification of storage rack. Let's say we call it storage rack 1, storage rack 2, storage rack 3. Right. So what would happen is it would store that partition server 1 is responsible for range A to B. Right. Now, and this A to B is present in storage rack 2. Okay. So partition server will use this information to connect to the corresponding storage rack and do the write operation. Yeah. So now what would happen is if one of the partition server goes down, the partition manager would say that partition server 3 went down. It was responsible for something. So the responsibility of partition server responsibility of partition server 3 now moves to partition server 2. So now partition server 2 is responsible for B2Z, which is present on SR1, for example. And so basically partition servers are just dumb API server sort of stuff, but these are like abstracted layer on top of it. But each partition server would have information to how it can connect to a storage rack or a storage layer. So this storage layer is not that abstract storage, but one storage layer is this. This is one storage layer, one storage rack.
So it won't affect the write. So
it doesn't affect the write. So what would happen? So the things, so you would have a crisis if a partition server. So basically what, if you see the evolution of the system, what it has actually tried to do is they've tried to defer the crisis, right? So for a service like S3, the crisis mode is when the data layer goes down, or when the data is lost, or when the data is corrupted, right? Until that point, if anything crashes, let everything else be scalable, correct? So each of the partition server, if this goes down, it should not have any effect. It should not have any effect on the data. But what's the crisis for this? If my storage rack goes down. So if my storage rack goes down, that is where you would have another storage rack having the copy of the data, and then it would point to this thing. Okay. So it's just that if you see from t equal to 0 to abhi tak ka discussion, the every time when we discussed about this, we have just tried to defer अपना crisis mode and just have कि सिर्फ इतना ही फटेगा तो देखेंगे. Till then everything else is okay. So if my partition server still goes down, it's still fine, because my partition manager can just change the setting and it would give that this partition is owned by this. Now if it is owned by this server, so now it will create connection to this and then start writing it over here, and then it would obviously have that mapping. This file is written on this storage layer on this disk at this offset, right? So something similar to that we discussed last week, right?
So I was just wondering why Google file system uses chunk concept to store, and here we don't use. I mean,
इसमें chunks होता होगा internally. I did not find it, but obviously कहीं ना कहीं तो chunks होते ही होंगे. मतलब otherwise you can't like if you have like 15 GB of file, you would not want to do that repeat upload from 0. So chunks तो होते ही होंगे. But वो उसका discussion we will anyway discuss chunking in 8th week का first day पे. कि how do we leverage chunks?
Yeah, so actually Dropbox has some their own S3 kind of storage, some pocket something.
Yeah.
So
they use chunks.
Yes, they use chunks something. Yeah.
We'll be exactly discussing Dropbox chunking approach.
Okay.
In Akamai also net storage basically, which is their S3 equivalent. Back in they also used to do chunking. मतलब बहुत detail I have read, but not sure. They had their own mechanism. They had their own RAID kind of system for the data and sending across.
See, chunks makes everything very efficient, right? You can have repeatability, you will have efficiency, you can have parallelism, right? It makes everything great, right? But then unordering of chunks, or rather handling unordered chunks, is a slight bit of challenge. But you know, that's the kind of benefits you get is it basically overpowers the cons that you have when you chunk. Everyone chunks it, but if I would have added chunks, if I would have, to be honest, I didn't find it in the paper. If it is there, it might be a miss from my end, but I did not find it in paper. So that's why I did not wanted to add that one more masala to this, right? So that's where if you'd want to implement chunking, you can do that. But since I did not find it on paper, I wanted to stay true to the source material. But the place that I'm definitely sure that chunking happens is with Dropbox, or wo will cover. But we can obviously do chunking over here as well. Nice. Any other question, guys?
Yeah, okay, so a bit irrelevant one, but like I just want to know like what are the different mechanism or tools you have used in your career when it comes to logging and monitoring?
Logging monitoring. Are ekdam ich tangent. Okay. Logging and monitoring. So started with so tools I used started with normal file. I used Greylog, Zipkin, normal ELK stack, and now we have just moved to Fluentd Pala stack, EFK stack.
Okay, and to show things like Prometheus or Grafana. Yeah, Grafana.
Grafana and Kibana. Logging के लिए Kibana looks good. Like you can use that जो है वो file by basically line by line and do query on that. Grafana पे Elasticsearch based visualization on Grafana is not good enough. So that's where Kibana for Elasticsearch based visualizations, which typically happens on EFK, ELK kind of stack. So that's where Kibana makes your logs look good. But if it's like pure analytics based use case where I just want to have like percentage of error rates and all of those part, I just use Grafana for that.
Grafana with Prometheus, right? For
Grafana with Prometheus or Grafana with Elasticsearch with aggregation queries. That also works. But not to like visualize log lines, but to do aggregations. For that, Grafana works well.
Yeah, thanks.
So there's a paper from Facebook, Scuba. I was reading. So they have this
what's the name? Scuba.
Scuba, yeah. Deep dive. They have given name. You analyze the problem. Scuba diving. So
scuba. Oh.
So it's very elegant paper actually. And there's one guy who mimicked the same thing. There's a YouTube video I watched yesterday, and they used Kafka and just file system to mimic the same.
Same as in this
Scuba functionality.
Oh, the Scuba functionality. Okay.
Yeah. So I read, but I may be.
I'll add you to Discord channel. You are not added now. I'll just send you the invite, and then you can share the resource there.
Yeah, sure.
मजा आएगा लोगों को जान के. Anything else? Anyone?
So even Facebook use this Scuba thing for their trending likes and all those things. So many things. Yeah. Apart from just this observability thing.
It's there for the visualization stuff or for logging.
Logging, visualization, and trending, and customer interaction, like, and what kind of mobiles and all decisions, everything.
Oh, yeah. Seems like a very heavyweight system.
No, it looks like it's a heavyweight, but the architecture is quite simple if you go through. Yeah.
Okay, nice. Thanks for that addition. Yes, this is nice. एक और चीज आगे we can read. Nice. Chalo. Okay. Thanks again, guys, for joining. See you guys tomorrow. We'll cover high throughput storage systems, and then DAGs architecture using Apache Airflow. Awesome. Thanks, guys.
Okay, thanks. Bye.
Bye.